Now let's start turning all of this into code. We'll begin with a small dataset loader that reads our text, tokenize it with a GPT2 tokenizer, and builds the XY pairs for training. We'll train on a single text file, the Epic of Gilgamesh, saved here as data/input.txt. We import the necessary packages. Dataset loader is a standard PyTorch dataset. It takes one argument, sequence length, which is how many tokens we want in each training example. First, we open the input.txt file and read the entire file into memory. Here we load the GPT2 tokenizer using TickToken. Inc.encode turns the entire text into a list of token IDs using the same vocabulary that GPT2 was trained on. We store all tokens in a single 1D tensor. Now, len function returns how many training examples we can extract. For each starting index, we need sequence length tokens for x and sequence length tokens for y, shifted by 1. And the total number of examples is length of tokens minus sequence length. The get item constructs one training example. X a slice of sequence length tokens starting at IDX. Y is the same slice shifted by one token. Now let's create GPT-2 model. This GPT class is our GPT-2. The constructor takes vocabulary size, which is the size of the tokenizer vocabulary, and embedding dimension. In the explanation of the architecture we used for, in practice, this is 768. Block size, maximum context length. End layer, how many transformer blocks to stack. End head, number of attention heads per block. Self-token embeddings, this is the token embedding table. Self-position embeddings, positional embedding table. Self.block, a list of block modules. Each block is one transformer block. We create n layer of them. Self.final layer norm, the last layer norm applied after all transformer blocks. Self.lm head, the output head. The forward method takes IDX, which is a tensor of token IDs of shape BT. B is the batch size, T is the sequence length. First, we compute positions. We also look up token embeddings. We add token and positional information. We then pass X through all transformer blocks. After all blocks, X is normalized once more, then LM head. This block is exactly one transformer block, like we showed earlier. In init, LN1, layer norm before attention, then the causal self-attention module, LN2, another layer norm before the MLP, MLP, the two-layer feed-forward network. In the forward pass, first we apply layer norm to X, then we feed that into self-atten. The attentions returns a tensor of the same shape as X. We add it back to X. This is the residual connection for the attention layer. Again layer norm, then MLP, then add the result back into X. This is the residual connection for the MLP. Now causal self-attention. We assert that n embed is divisible by n head because each head will have dimension n embed divided by n head. We define key, query, and value, and projection. Then we create the causal mask. Torch.trail creates a lower triangle matrix of ones. Everything above the diagonal is 0. We reshape it into shape 1, 1, block size, block size. X has shape B, T, C. B batch size, T sequence length, C embedding dimension. First we compute Q, K, V. Then we reshape into heads. Next, we compute scale dot product attention. We divide by square root of head dimension. Now we apply the causal mask. Whenever the mask is 0 above the diagonal, we set the score to -infinity. We then apply softmax. Then we multiply by V. We then rearrange and merge heads back together. Finally, we pass through self.projection. Now MLP. In the constructor, self.c fully connected is a fully connected layer from nembed to 4 times nembed. Self.gilo is activation function commonly used in transformers. Self.projection, a projection back from 4 times nembed to nembed. Now we define all the important hyperparameters in a single configuration file, config.yaml. This makes it easier to tweak values without touching the code. Now let's go to training script. This function handles command line arguments. We create an argument parser. We add a single argument, config, which is the path to our YAML configuration file. It has a default value, source/configs/config.yaml. So if we don't pass anything, it will use that file. In main function, we call parse arguments to get the config path. Then we open that YAML file and load it with yaml.saveload. Here we read all the values from hyperparams in config.yaml. We check if a GPU is available. If yes, we train on the GPU, otherwise use CPU. Dataset loader, read dataset file, tokenize it, and creates XY pairs. Data loader wraps the dataset and give us shuffled batches of batch size. We create our GPT model and then move it to the correct device, CPU or GPU. We use ADAMW, commonly used for transformer training. Betas and epsilon are standard values for stability. Finally, we call the train function. This function performs the actual training. Len trendloader.dataset is the total number of XY pairs. Dividing by batch size give us approximate number of batches per epoch. We loop over the number of epochs. X and Y are token ID tensors from dataset loader. We move them to the correct device. Model X produce logits. Then we compute loss, zero grad, clear previous gradients, loss that backward, compute gradients of the loss with respect to the all model parameters using backpropagation, optimizer.step, update the model parameters. After every epoch, we call save checkpoint function. It saves the model weights. Let's run training. Alright, I trained for one epoch and I've saved the checkpoint. Now it's time for the inference part. This is just simple script to run inference. That's basically how GPT-2 works under the hood. Thanks for watching.